Now we can actually track the electron flow in redox reactions by assigning another type of hypothetical charge. In the past, we've talked about formal charges, which is a hypothetical charge that we assign to covalent compounds in order to justify double and triple bonds that we assign and to make the most stable, probable structure of that compound. When we're talking about electron flow, it is in our interest not to assume that the electrons are shared between elements, but that they're fully transferred. Now, given that electrons themselves are charged particles that are arbitrarily given a charge of -1, we can safely assume that if there is a transfer of an electron from one atom to another, there's similarly a transfer of a negative charge from one atom to another. And the more electronegative atom is going to be the one that removes or gains those electrons for itself. And this gaining of electrons is going to influence not only the charges that the element itself carries, the highly electronegative element, but also any other element that it's bonding with. And so, based on electron transfer and kind of keeping budget of what is happening with the electrons, how many are coming and going, we assign a hypothetical charge called an oxidation number, or in some textbooks called the oxidation state. And so the oxidation number is the charge that an atom would have if all of its electrons were gained completely or transferred or lost completely. There is no partial exchange of an electron. There's either a full gain or a full loss of an electron. And based on that, what is the hypothetical charge that your element should have? In short, while formal charges relied under the assumption that bonds in a covalent compound are perfectly covalent, that is, that the electrons between the bonding atoms are perfectly and evenly shared, oxidation numbers run under the assumption that pure 100% efficient ionic compounds or ionic bonds are formed. That is, that the electronegative atom, the highly electronegative atom, completely removes the electron from the more electropositive atom or the least electronegative atom, forming a 100% purely ionic bond. Now, if your oxidation number is positive, or you have a positive oxidation state, that means that electrons have been removed from the element. If your oxidation state is negative, or you have a negative oxidation number, then that means that electrons have been added to that element. If your oxidation number is 0, or we would say you would have a 0 oxidation state, that means that the element is likely in its elemental form and that there has been no electrons gained or removed. So why do oxidation numbers matter? Well, first thing is, by tracking the changes in oxidation numbers in a chemical reaction, we can identify what gets oxidized and what gets reduced. This also helps simplify our understanding of electron transfer when we're writing out complex equations or reactions, and not just of the famous 5 reactions in standard chemistry. And furthermore, we use these oxidation numbers to balance redox reactions, especially in neutral form. So there are some rules for assigning oxidation numbers, and there's a lot at first, but if we follow these rules and repeat with practice, they will come like second nature. The first rule is that any element by itself, or that's in a ground state that is unbonded with anything, has an oxidation number of 0. The second rule is that any metals in group 1 always have an oxidation number of +1. So that's in 1A over here. Any metals in group 2 or in 2A have an oxidation number of +2. And then any metals in group 3 have an oxidation number of +3. The third rule is that the oxidation number of a monoatomic ion is always equal to its charge. So for example, if I have the sodium ion, so Na+1, then that also has an oxidation number of +1. If I have a chloride ion, for example, with the elemental form of Cl-, indicating a -1 charge, then that would have an oxidation number of -1. The fourth rule, which is probably one of the more common rules in this set, is that the oxidation number of a nonmetal in an ionic compound must equal to its charge. Now, Rule 5 is probably the most used and important rule for assigning oxidation numbers, and that is that the sum of oxidation numbers in a compound, no matter how complex that compound is, must equal the charge of the compound. And in most cases, that's going to be 0. And again, this is the most used rule. What I say to most people that are doing this for the first time is, if you notice that none of the other rules apply, you're probably going to need to exercise Rule 5 for that particular element. And then Rule 6 breaks down into 3 categories. So fluorine is always -1. It's the most electronegative element, so it's always going to be -1. Oxygen is usually going to be -2, except if it's bonded as a peroxide, like hydrogen peroxide, or if it's with fluorine, then in both of those cases, it's going to be -1. And then hydrogen is usually going to be +1. The exception is that if it is a hydride in an ionic compound, so if it's bonded with a metal, for example, CaH2, then it's going to be -1. So using the rules that we outlined previously, we're going to determine the oxidation numbers for the elements in each of these compounds or multivalent ions. So if we start off with sulfate here, we're going to do with the rules that are most obvious. And that's what I always try and do here. The ones that are, like Rule 6 and Rule 3, etc. So for Rule 6, we see that oxygen is going to be -2 unless it is bonded with a peroxide, which in this case it's not. So it'll be -2. Now, there are 4 oxygens here. So that means that the total oxidation number or total hypothetical charge is going to be -8. Now, if we go through the rule list, we can see that there are none that directly apply to sulfur in this case. And when that happens, when there's no direct rule that applies to an element, then you know that you're probably going to have to deal with Rule 5, which states that the sum of the oxidation numbers in all of these elements in the compound must equal the charge, in this case, -2. So the way I think about it is, if I think about sulfur as X plus -8 is going to give me -2. Well, if I isolate for X by adding 8 on both sides, that would make X a total of +6. So then if sulfur is +6, and we go +6 plus -8, now each oxygen is -2, but the total makes it -8, then that would allow us to have a charge of 2 negative. And so by virtue of Rule 5, sulfur has a charge of +6. And Rule 6, oxygen has a charge or an oxidation number of -2. So now, if we look at ammonia here, again, Rule 6 makes it known that hydrogen is always going to be +1 unless it is bonded to a metal to make a metal hydride. Now, that is not the case. Nitrogen is not a metal. So this will be +1 by virtue of Rule 6. Now, remember that there are 3 hydrogens here. Each one of them is carrying that +1 charge. So we're going to write +3 in brackets. And then if I look through the rules again, your nitrogen here is not a monoatomic ion. It is not an element that's in its ground state or that is 0, right? Or that is by itself. And it's certainly not an ionic compound. So none of the rules directly apply, which means that Rule 5, once again, is likely going to be exercised. And so we're going to figure out, well, what oxidation number does nitrogen have to have in order for this entire compound to equal a charge of 0. Remember that if charges are not listed, that means it's 0. So we're going to go X plus, and the total of the hydrogens will be +3, and that's supposed to equal 0. So if I isolate for X, I would see that X is equal to -3. So by virtue of Rule 5, your nitrogen here is -3. So now following the same trend here, we're going to start off with the rules that are most obvious. So that's the oxygen here, -2, which in total is going to be -8. And your potassium, okay, is +1. And it's +1 because remember, like in the previous rules stated, any element in group 1A is going to be +1. 1. And that is by virtue of rule 2. And so the only one that we don't really know that there's no direct rule for is manganese, because it's not in groups 1 to 3, and it doesn't allow for rule 6 to be used at all. So whenever we don't know which rule directly applies, or whenever, I should say, there doesn't seem to be any of the rules that directly apply, that means that rule 5 is to be instated. So for the last one here, iron 3 oxide, using the oxidation number rules above, I want you to try this one on your own and then unpause the video and see if you got the same answer.